Hello everyone and welcome to your Chem 113 review on enthalpies of formation. My name is Jason and I work for the ASU Tutoring Centers. So first let's set up the reaction that we're going to be working with right now. We're trying to calculate the standard enthalpy change for the combustion of 1 mole of benzene, C6H6, to carbon dioxide and water. So we're taking benzene, we're combusting it with oxygen to produce for us carbon dioxide and water. And I gave you, I balanced it already for you, so you don't have to worry about that. Remember, typically we don't like fractions in our equations. However, in the case of combustions, fractions are often used so that we only have 1 mole of the thing we're trying to combust. That's just a common rule in chemistry. So what we're using here is we are using these heats of formation or enthalpies of formation. What is that? Well, an enthalpy of formation, it's the enthalpy change, so it's the delta H associated with forming a compound from its constituent elements. Constituent elements. What the heck does that mean? Also, this looks like a weird delta H. Messy handwriting today, apparently. Delta H, it's better. So what this means essentially is like, let's take the benzene, for example. If we wanted to form benzene, we're taking 6 carbon atoms and we're reacting them with 6 hydrogens, which in reality would actually be like 3 hydrogen gases, because again, hydrogen is a diatomic. And together this gives us C6H6. So we're breaking down the constituent elements, the carbon and the hydrogen, and imagining what that would look like as those individual elements form together to produce benzene. And the amount of energy that is either required or released for this reaction to occur is given by the delta H sub F. Okay, so that's what a heat of formation is. Now we can use heats of formation to determine overall enthalpies of a reaction. And the general rule for that is, if you wanted to find the delta H of, say, this reaction above here, or really any reaction at all, the delta H would equal the heats of formation for the products minus the heats of formations of the reactants. Because think about it, when this reaction is occurring, what are we doing? We are forming carbon dioxide and water, so our products, we would use the normal heats of formation because we're forming them. However, the reactants are things we're breaking apart, right? We're breaking the reactants apart to form the products. So we wouldn't use the heats of formation for the reactants because we're not forming those. We're breaking them apart. So we would use actually the negative of the heats of formation, which would represent the heats of, breaking apart. Okay, so some things to note before we jump into this. We're not just asking for the enthalpy change, we're asking for the standard enthalpy change. What does that mean? Well, standard enthalpy change is actually given to us by that little circle over the delta H. You may have noticed over some of these heats of formations, we have this little circle. And what that means is that it is a standard enthalpy change. So standard enthalpy change requires the following 4 things. Standard enthalpy change. So in order to be considered a standard enthalpy change, first, gases are assumed to be ideal. Ideal at a pressure of 1 bar. Okay, exactly discussing what an ideal gas is something we'll save for a different video, but the idea is it acts perfectly as a gas as we would like one to. So it has, The gas particles never collide with one another. Each individual gas particle doesn't really take up space. Things like that. Again, I'm not really going to go into the details of it, but the gases are assumed to be ideal and the pressure is assumed to be 1 bar. Other thing we need, if we're doing it in solution, the solutes are in ideal solutions. And in the case of solutions, ideal essentially means concentration or molarity of 1 molar and pressure of 1 bar. Okay, third thing to note, all liquids and solids are pure. Under 1 bar of pressure. And the last thing to note, all elements are in most stable form. Under 1 bar of pressure. And bar is just a measure of pressure. There are several different ways you can measure pressure, and bar is one of the units that can be used. So these are the 4 cases to be considered a standard enthalpy change, and it really just depends on what things you're working with. If you're working with gases, they need to be ideal. If you're working with solutes, they need to be in ideal solutions. If you're working with liquids and solids, they need to be pure. If you're working with just elements by themselves, they need to be in the most stable form that they can exist in. So for instance, we can't just deal with oxygen by itself, just O, because that's not its most stable form. Its most stable form is O2. So all these things need to be met in order for a reaction to be considered standard. Okay. Cool. So just keep that in mind. I mean, it doesn't really affect too much like the work we're doing, right? We'll still calculate the enthalpy change using that products minus reactants thing, but just keep in mind exactly what we mean when we say standard. The other thing to note is, although we're given 4 different things here, including like oxygen gas isn't given a heat of formation. And that's because O2 is the common form of oxygen, right? It's a diatomic molecule, so it's most commonly in the O2 form. That means that the oxygen gas doesn't need to form. You know, the delta H sub F of O2 as a gas just doesn't exist because we kind of just assume it's already in this form. So it doesn't have a heat of formation, we just assume it's 0. Okay, now we get to put everything together now. So we're going to use that idea of products minus reactants. And we have to also take into account how many moles of each product and how many moles of each reactant we're using, right? All of these units are in kilojoules per mole. So if I have 27 moles of benzene, I'll have to multiply my delta H by 27. So just keep that in mind as we go through this. So the overall delta H of the reaction, which we'll write as Rxn, and again, we're looking for the standard enthalpy change, so we need to put that little circle above it. As mentioned before, it's products minus reactants. Okay, and when I say products minus reactants, I mean the heats of formation of products minus the heats of formation of reactants. So let's look at my products. I have carbon dioxide gas, so I need 6 times the heat of formation of carbon dioxide gas. Again, because there's 6 moles and these are kilojoules per mole. And then I also need 3 times the heat of formation of water. Okay, so these are my products. And then I need to subtract off the reactants. My reactants are benzene, and I only have 1 mole of it. And my other reactant is oxygen. So I need to put in the heat of formation of my oxygen gas times the 15 halves, because that's how many moles I have. Okay, now we substitute the numbers in. So the heat of formation of carbon dioxide negative 393.5 kilojoules per mole. The heat of formation of water is negative 285.8 kilojoules per mole. Heat of formation of benzene is 49 kilojoules per mole. And the heat of formation of oxygen is 0 kilojoules per mole. Okay, multiplying everything, subtracting, simplifying, we get negative 3267 kilojoules. The reason it's in kilojoules is because, again, we were taking kilojoules per mole, but we multiplied by the moles of each of them that we had in our equation. Those are what those coefficients were out front. All right, cool. Thank you for watching. That's all I have for you. If you want more information about the free tutoring services available on all 4 major ASU campuses and online, please check out tutoring.asu.edu/content/tutor-search. By going here, you'll be able to find a tutor on your campus or online that is able to help you with your specific classwork. So again, thank you for watching, and I hope you have a wonderful day.